today's presentation is on the Hadean. And the Hadean kind of kicks off everything we know about Earth history. So we're getting into the meat of the course here. So the Hadean and the early development of Earth. How did things all start? Well, actually, it's not our fault. It's the sun's fault, kind of. We are, one of the satellites of the sun, essentially, is what you could say. We're really a planet that's revolving around the sun. There are 8 of us in this family. And the sun's pretty, medium-sized sort of star. We're out in the end of one of the spiral arms of the galaxy that we know as Milky Way. So really, much of what we understand about Earth has to really come from what we know about the origin of the sun as well. So most stars are made out of hydrogen. That's, in fact, how they usually start anyway. And under extreme pressure, they're actually a glowing ball of plasma. Plasma in the sense that they are not a gas. They are actually mostly the nuclei of these sorts of elements that are in a star. And so the electrons are actually spun off, they're given off as photons and things like that. So most stars are made out of hydrogen, but the hydrogen's under so much pressure, in fact, that it went critical, and then fusion began. So fusion's where you can take 2 hydrogens and turn it into a helium. You squeeze them tight enough, and then you begin to develop these other subatomic particles. And if you give off certain particles out of let's say a proton, you're gonna form a neutron, right? So you give off the part that the positron, and so these sort of particles are actually pretty convertible. So you can turn a proton into a neutron, and a neutron you can turn back into a proton if you do the right things to it. But anyway, we start with hydrogen, and hydrogen becomes helium next. And helium can also be fused, as it turns out. In fact, most elements can be fused to a certain extent. So as they expend their hydrogen, they go to a helium sort of phase after that, and they become red supergiants. And so, for example, a red supergiant would include stars like Betelgeuse. If you look in the night, in the wintertime, in the night sky, you'd see the constellation Orion. Betelgeuse is the upper left-hand side, kind of like the part of one of the hands, I guess you could say, sticking up out of Orion, north of the belt, for us anyway, in the northern hemisphere. And that's Betelgeuse. Rigel's the one that's out at the other end, opposite of that, and that's a blue star. But Betelgeuse is a supergiant, really huge, and not that far away from us either. So we always are concerned about Betelgeuse. So that is, probably burning helium. We can find out what these stars burn by using a spectrometer, and so you can get the absorption bands essentially and tell what the elements are in any individual star. You can go to carbon next. So if you go to hydrogen and then to helium, then you can go to carbon. So there are carbon stars out there. I don't know of any personally, but I'm sure they're out there. And then there are other ones that go from carbon to the next phase, which is neon. And then eventually you can get to a silicon star as you begin to fuse these particles together, right? And you're forming larger and larger nuclei in that plasma that forms that star. And eventually you get up to iron. And so iron is odd. You can get to iron and the reaction will change, let's say. Well, it's not going to stop. It's going to change. Iron fusion actually requires energy, whereas all of the other fusion products, if you take, for example, the hydrogen bomb, where you're making helium out of it, that radiation that you get out of a hydrogen bomb is from the power or the energy that is given off in that reaction when you turn hydrogen into helium. When it comes to iron, however, it requires energy to fuse, and so therefore when it gets to iron, usually these things will either turn into a dwarf, they actually squeeze down and turn into something that's super, super dense, or they blow up. And so that's, they kind of leave the nebulae behind then. Nebulae, plural for nebula, which is a dust and gaseous sort of cloud that's left behind when stars explode. So there is a nebula also, the let's see, it's the Orion Nebula in Orion. And so if you look at the knee on the left-hand side, so if you go from Betelgeuse, which is up at the top and up the left, you get to the belt, and then you go down to the left-hand side there. Right there in the crook of that left-hand side is the Orion Nebula. So if you ever get a chance, take a look with a nice telescope, and you'll be able to see that nebula, no problem whatsoever, if you have the right magnification and clarity. So if we had all of those elements up to iron, let's say, so okay, if we know the sun is mostly hydrogen and fusing and giving off energy all the time, why do we have all of these other elements in Earth? So we have things, obviously, you guys already know the top 10 elements, right? In the Earth's crust, that's oxygen, silicon, aluminum, iron, calcium, sodium, potassium, magnesium, titanium, and hydrogen. All of those elements right there make up most of the Earth's crust, and that's the top 10 out of the wide variety. What about, why do we have all of these elements if the sun was made out of only hydrogen first? Well, the answer is that it wasn't. It was made out of dust from perhaps as many as 5 stars that dust had coalesced together, and in the center part, that's where the sun was. And so where the sun is, we have we have gold in the sun. There's all these other elements that are in there, but by and large, it's mostly hydrogen. And the reason for that is Earth probably had those same elements with a lot of hydrogen, but when the sun fused for the first time, they call it ignition, when it torched up, when it lit up, it probably blew off most of the hydrogen and most of the other gaseous material that would have been around the core of the Earth. And so just the heavy things got left behind on Earth then. So we are made out of stardust. We are made out of the remains of 5 other stars, which is kind of cool because Crosby, Stills, and Nash recorded that on the Deja Vu album, 1970. We are stardust, we are golden, and we got to get ourselves back to the garden, so they would say. They would sing anyway. And but anyway, it's actually accurate. We are made out of the materials of other stars that have gone before. So in other words, the star is not a first-generation star. Our sun, Sol, is not a first-generation star. It, in fact, is only a little less than a third the age of the entire universe. And so if the universe is like 13.7 billion years old, our sun is the same age as the Earth, 4.567 billion years ago is when it formed, when it ignited pretty much for the first time. So if we look at a collection of stars and how we can rank them according to their brightness and the evolution that they go through, we're right about in the middle here. So if you look for the sun on this next diagram here, you'll see that the sun is right there, pretty much in the middle of it all. And you can see all the other stars that are around us there. So the sun is like right there, close to where it says, what is it? I can't read it from my screen here, but the sun's right in the middle there. And we're a middle-aged star, as it turns out, too. So in the evolution of stars, we are about halfway through the production of all the energy that the star is going to give off. And eventually, the sun will probably expand and expand and expand, trying to make it to the red giant stage, although it probably will fizzle out before that and become a white dwarf or something like that. So in the beginning, when we look at the origin of the Earth, in the beginning there was this glowing cloud of matter that gathered together due to self-gravity, and we had a sun that came out of that as well. So the sun was the center of it. And that's where the major mass is, of course. And the dust and gases gathered together in this giant cloud. And they call this the nebular hypothesis, by the way. So it was a nebula first, that dust and gaseous cloud. And all that material began to spin then. So as you spin, you're forming this sort of proto-planetary disk. An accretionary disk is what they call it, in fact, in astronomy. And the planetesimals would be little tiny planets that would have circled around the sun. They would have clumped together and had their own self-gravity and collected some of that dust material into their compositions. And they would grow up to about 1 kilometer each. And then Once you get past 1 kilometer, things go crazy and you get what they call runaway accretion. So the gravity is enough that you begin to hoover up all of the material around you. And so as these things are rotating around the sun and spinning themselves, they're gathering a lot of energy. They're getting, angular momentum and so forth, but they're spinning around, and then boom, all of a sudden the sun ignites because it has enough enough mass to be able to do that. And instantly, the outer parts of all the inner planets, we think anyway, was gone in that explosion when we finally had a thermonuclear explosion. And of course, the sun ignited. And but the outer planets didn't experience the same sort of effect. And so in the outer planets, you have the gaseous giants, not close enough to the explosion to blast away their atmospheres. Most of Earth's atmosphere was gone in that ignition. And the very farthest stars, then, the farthest planets and planetoids that were out there would be frozen, in fact. So many of them were like so far out that they actually are not near, absolute zero, but, they're pretty cold compared to Earth, let's say. So on the next slide, you can actually see an artist's rendition of what probably happened with the nebular hypothesis. If we have a gas cloud, turns into that accretionary disk, and that disk begins to form isolated areas that are where the planets are sweeping up materials, and eventually it's going to give us the planets here. And so on the next slide is just a comparison of the sun size with the smallest of the inner or terrestrial planets, as we call them. And the terrestrial planets include Mercury, of course, Venus, Earth, and Mars. And there's Mars, you can kind of tell by its size. Now, there's a sunspot on the sun that's actually larger than Mercury. So Mercury cuts across, and they call that a transit when it goes across the face of the sun. And that happened not too long ago here, but, NASA is able to take photographs of these things. And so there you can see Mercury in the circle there. Now, if we compare the inner planets to one another size-wise, these are all the correct size, essentially. So if that's Mercury up there at the top, you can see it in the little dot on the face of the sun there compared to the size of the sun. Mercury compared to Venus is about, if you go up to Venus is almost as large as Earth, in other words. And Mars is substantially smaller than Earth, right? So about 60% of the diameter, or it's the diameter, not the radius. So and so you also see the Venus is pretty close in size to Earth, and so we got the bulk of the terrestrial planets wrapped up with those two planets, Venus and Earth there. Venus extremely hot, and then Earth, was right the nice spot, I guess you could say, and Mars not so hot, pretty chilly actually if you get to Mars. If we go on our excursion a little bit farther, you can see another photograph of the sun here from the X-ray band, I think it is that one. And you can see that there's texture on the sun. They call them granules, I think, or granulose texture on the outer regions of the sun, the outer part of the sun that forms the corona, then the glowing part around the sun. If we compare the sun to the size of Jupiter, now that's a 1-to-1 comparison there. So there's about 16 Jupiters across in the diameter of the sun. And Earth is shown compared to Jupiter in that top vignette there. So you can see the size relationship between Earth and, I think it's 16 Earths actually that go across Jupiter. Diameter-wise, so 16 times larger diameter on Jupiter than what Earth is, and I think it's only like 8 Jupiters across will give you the diameter of the sun. And Saturn's about the same size as Jupiter, not quite as big. And then next you can see Uranus. Uranus, like Saturn, has a ring, but they don't show the rings on this one because they're not quite so pronounced as the ones we see on Saturn. And because this isn't an astronomy course, we're not going to get too deep into what the composition and structure of each of these are. But Neptune, pretty cold. And when you get out there to, Uranus and then Neptune, the last two out there of the 8 planets, there we have it. Pluto is no longer considered to be a planet. It was kicked out of the club for not being large enough, not having the right composition, and having a strange sort of orbit around the sun and so forth. So they demoted it to what's called a minor planet, or probably not a PC sort of term, a dwarf planet. We call. I don't want to get into that, but as dwarfs are small, right? And so minor planets. And so that would also include Ceres, which is in the asteroid belt, and it's 475 kilometers in diameter. And then Eros, there's Haumea, I think it is, Haumea, Maki, and Pluto. Those are the larger of the minor planets, or what some people call dwarf planets. And there's some other ones too, like Vesta. Vesta is in the asteroid belt as well. It is not round like the other planets. So some of the minor planets, you can actually see their shapes up here and so forth. So Eros is there that has some moons around it. Pluto is there with its 2 moons, Charon and Hydra. And what's the other one there? Nix, is it, I think? And Ceres, by comparison, is actually larger than what Pluto is, right? And yet it's in the asteroid belt. It's composed of asteroids, right? It collected up a whole bunch of asteroids after that pseudoplanet blew up, essentially, or was ripped apart by the tidal forces of Jupiter. And we're going to talk more about that, actually, too. If we go to all these other ones like Vesta, it's not round, but there's 200 other objects besides Vesta that are in the asteroid belt that are fairly large. If we go to other star systems, if we go out beyond the solar system, there are approximately 4,000 planets that are now known outside of our solar system. So it gives us hope that there's actually life relatively close by, because those are the only ones we can detect anyway, that they have planets. So we look at the sort of like anomalies in the light and so forth, and people were able to detect those all the way into I think it was the late 1990s when people first began to find planets around other star systems. Most of these planets, of course, are round, and they're not flat. Oh, yeah, I don't know. Okay, that's pseudoscience there, and it's not even science, really. It's a myth, right, that people make up because people love conspiracy theories, right? They shouldn't. Okay, but, some of them are really, really poorly founded. Why do people think that? I don't know. So self-gravitation pulls this material together, just like in the original part for the nebula that came together in the sun. So also larger bodies will pull things in and accrete material into their structure as well. So there is a certain point in when you have enough material that you get gravitational relaxation, and those materials will it'll smooth out the topography, and things will become rounded, essentially. And so you may get some highs and lows, of course, on that thing, but it's going to be fairly round once that gravitational relaxation occurs. And so the topography kind of evens out a little bit. And when it gets to that point, they call it hydrostatic equilibrium. It develops its maximum rounding at that point. So that's the story of some of the planets and how they are, regarded anyway right now in our solar system. Now, I've got an interesting little tidbit on the side here to tell you about. Now, it's still important to know. It's called the Titius-Bode law. And I'm going to go through the sequence first, and it concerns the planetary spacing. How are the planets arranged in the solar system? If we took a sequence of numbers, and we're just going to pull out a 0 to begin with, but you add a 3 to it, right? 0 plus 3 is equal to 3. 3 plus 3 is equal to 6, right? And so if you have 6 plus 6 is equal to 12. 12 plus 12 is equal to 24. 24 times 2, 48. Times 2, 96. Times 2, 192. And then times 2, 384. You're just squaring it as you go along, right? So, but you start with 0 and 3 first. And it was Titius and Bode who came up with this idea. Now, if you add 4 to each one of those, so 0 plus 4 is 4. 4 plus 3 is equal to 7. 4 plus 6 is equal to 10. 4 plus 12 is equal to 16. 4 plus 24 is 28. 4 plus 48 is 52. You get the idea. We go up to a 100, 196, and then 388 is the last in that sequence then. Now, if you divide that by 10 each one, right? So if we divide it by 10, you've got 0.4, 0.7, 1, 1.6, 2.8, 5.2, 10, and so forth down the line there. Now, the 1 in this sequence of numbers represents the astronomical unit of, well, it's the astronomical unit that we define. It's the distance from the sun to the Earth, center of the sun to the Earth's orbit, right? That's defined as 1 by just pure convention, so that's 1. As it turns out, 0.7 is the distance, the number of astronomical units it is to the orbit of Venus. 0.4 is roughly the distance to the orbit of Mercury. And the actual distance is actually shown in astronomical units here on the next part of this list here. And you can see Mercury's 0.39, Venus is 0.72, Earth is 1 by definition, Mars is 1.52, which is close to 1.6. And then what's the next one? It's 2.8, right? But there is no 2.8 astronomical unit planet. There is, however, a 5.2 astronomical units, and you're out in the orbit of, the revolution, the orbit of Jupiter at that. Instead of 10, we have 9.54 for Saturn. Instead of 19.6, we have 19.19 for Uranus. Instead of 38.8, we have 30.44 for Neptune. So what is that missing 2.8? That's the asteroid belt. And so the asteroids you can see over here are shown in this diagram, and it's astronomical units at the bottom there. And the diagram shows you the red areas in there and the blue areas. And the red areas, I think, are called the Trojan asteroids or the Trajan asteroids. And so there's two different clumps of asteroids, essentially, that go around on either side of Jupiter and orbit roughly in that sort of capacity around the sun. And so that goes between 2.1 out to about 3.2 there. And so the 2.8 would be roughly in the middle of that. And so that's one of the rationale, one of the reasons that people explain is like why the asteroid belt is there. And you already know that there's a substantial amount of material in there. Some of it gets disturbed by the planet Jupiter is enough to like draw and make the orbit more elliptical in many of these things. And of course, some of these things then cross the Earth's orbit. And when that occurs, that could be a very dangerous thing. We had one just recently go by the Earth at 13,000 kilometers, I think, something like that, which is really, really close. We know that these things wiped out the dinosaurs, for instance, as well. So it's something to pay attention to. For the most part, most of the objects in the solar system were kind of swept up by Jupiter. We got to see that actually firsthand in 1994 when the Shoemaker-Levy 9 comet, actually it was 1993, the Shoemaker-Levy 9 comet whizzed by Jupiter and broke up. And when it broke up, it came around the sun and then collided with Jupiter on the next year in 1994. So there were 22 pieces of the Shoemaker-Levy 9 comet that broken up comet that impacted Jupiter. One of the most spectacular events in history, for watching that on in real time. The first time the internet had been used to distribute NASA images, and so you'd sit there and watch where every line of your monitor would like stitch a new one, and you'd see this giant explosion on Jupiter related to that impact. Some of those explosions were like the size of the Earth. Okay, so that's how Earth got its start. And you know where we're at, and you know that there's stuff out there that got swept up. And so, in fact, it didn't stop once the sun had ignited. We were still sweeping up stuff for a while. And so the Hadean is that first time period. And so the Hadean stretches from 4,000 to 4,500 roughly to 4,000 million years. Okay, so in other words, 4.56 to 4.0 billion years. And it's named for the god of the underworld, the Greek god of the underworld, Hades. And of course, that in other, it's referred to as hell in other places, right? And so that's why they call it the Hadean, because it would have been pretty horrific to have been on Earth back then. It would kill you pretty quickly. There were a few rocks back then, as you well know. Some of them date back to Hadean time, and you've learned most of those already. There were some early zircons that go back 4.4. There was the 4.28 and that early ocean crust that had formed. So there was water here in 4.28. There had to have been water here in order to have ocean crust, okay? And then also there was also a 4.03, right, was that the cast of gneiss. And so all those things are in Hadean age, right? Although most of the rocks around them are actually Archean. So with that roughly 4.5 billion year age in mind, we don't find anything older than 4.4 so far on Earth. And the idea is that there was a large planetary body that nearly struck Venus, okay, and probably could have struck Venus actually and caused its orbit. Venus, unlike any of the other planets, actually rotates backwards. Okay, so if you're on Venus and watching a sunrise, you'd have to look to the west, instead of to the east. And so that's how much that impact affected the rotational aspect of Venus. And there's other planets that have other sorts of anomalies like that. I think it's Uranus that's been knocked sideways. And so Uranus is like spinning, but spinning towards like their north is pointed off towards the direction that the planet actually revolves around the sun. For Earth, we got hit too early on. So like 4.5 billion years ago, we got nailed by a Mars-sized planet. And people have regarded it and have named it even. They call it Theia. And so when Theia hit the Earth, part of it stayed with the Earth, gave us a lot of rotational spin. And what it did, it took a lot of that debris from that impact and formed another planetary body around us, smaller than Theia was, but big enough that it would actually orbit the Earth. So it got locked in orbit around the Earth. Locked meaning that it doesn't rotate itself. It actually rotates at the same velocity it orbits the Earth. So we always see the same face of the moon because of that. And it's the locking of that orbit. Yeah, I think I put some links into this as well. One of the other interesting aspects of that collision that formed the moon, because the moon's made out of the same material that Earth is made out of, they went up there and they found a northite. They're the same type of rocks that we find on Earth. They know this is called a hypothesis. It's called the Big Splash or the Giant Impact Hypothesis. Now, if you take that, the moon is actually not just locked in orbit around the Earth with the same face pointing towards us all the time. It also is getting farther away. So it's actually slowly getting farther and farther, like 3.8, I think it is, centimeters per year, that it's actually drifting away from Earth slightly farther. So in other words, you don't have to go back that far, and the moon would have been right there, right next to Earth. So there must have been enormous tidal effects that the moon caused on Earth. We certainly caused that on the moon as well. So after that impact, if that impact was at 4.5 and we got rocks that then began to form after that, right? So that 4.4 zircon, just a few 100 million years after that, right? So 100 million years later, boom, your first magmas were crystallizing with things like zircon. And even at that time, there was still what they call the heavy bombardment. We were still sweeping up these fairly large, sort of like, less than a kilometer size impactors, and boom, they'd hit the Earth and become part of the Earth then. And so we accreted a lot during that time. So that happened, in fact, from 4.5 well, actually the age of the moon. Okay, so 4.5 to 3.18. But we kept taking all of that material for a long period of time into the pretty much to the end of the Hadean. I think we were still sweeping up a lot of debris. And so when we finally got a lot of this debris together, now remember, we're kind of molten almost to that point, right at 4.5, especially after that impact. So the next thing that happened, of course, is you begin to like cool off, and then you crystallize these things. And then eventually we're going to form some of those materials, right? Even though very once in a while we're getting bombarded. People have suggested that we may have had magma oceans first during the Hadean, but then water would have formed a little bit later on during the Hadean. And so that's when you get, finally towards the end of the Hadean, 4.28, you're actually having ocean crust on the Earth. And so those are those old rocks down here at the bottom. Now, the other process that's going on after we got bombarded with all this material. Now, as far as we know, most of the impactors that strike the Earth today, the asteroids, we call them meteoroids because we don't know where they come from necessarily, because they could come from any planetary body. We get some from Mars, we get some from the moon, we get some from the asteroid belt. Some of those are nickel iron. And so that nickel iron would have accreted to the Earth. And so there was already iron and nickel in the Earth already. So what happens is if you take all those heavy substances, they go to the center. So the heavy substances would sink to the center, and they call that differentiation. So as everything moves to the center after the moon had formed, we get a core. We get first a very slowly crystallizing inner core. And of course, we know that outside of that, we still have a liquid outer core. And so, but it would have been molten to begin with. And so the inner core would have been molten still back, 4-point-some billion years ago. So we have these other rocks that form on the outer part of the Earth, and the Acasta gneiss, the Jack Hill's metaconglomerate is much younger, but some of the zircons in it were actually derived from some of the first magmas that crystallized on Earth. The next slide actually shows you where that is again. I think you've already seen some slides of the Jack Hill's conglomerate, as I recall, in the absolute age dating presentation. But here you can see on a map, on a satellite image of Australia, you can see the range where the Jack Hills are out in the western part. Not that far away from an area called Shark Bay. And I think we talked about that with the, at some point we have in here anyway. Or maybe not. Maybe we will anyway. I know we're going to talk about Shark Bay. That's that little peninsula that sticks out west of Jack Hills there on the continent of Australia. You can see what the Jack Hills look like in person there on the bottom there. Now, I've not been there. That's somebody else's photograph, but it's a pretty desolate sort of place, the western desert of Australia. And the rocks out there, they've been metamorphosed, of course, around the perimeter of what would have been a smaller craton. There's several cratons in Australia. That's just one of them right there. So here you can see also the Jack Hill's metasedimentary rocks are mostly about 3 billion years old, but there happens to be one zircon that is actually 4.4. If you took an average of the consistent age dates that people get off of it, it's much closer, in fact, to being 3.75, which is, of course, an Archean age. So the steps that it has to go through, right? So first you have to have a magma that cools to the point where you can actually form zircon. That zircon is incorporated into an igneous rock. That igneous rock had to have been uplifted, eroded, uplifted and then weathered, and for what kind of weathering you would have back then, and eroded, and then deposited in a conglomerate. And then that conglomerate at some later point had to have been metamorphosed, and so that's where you get the metamorphic sort of content. Now, that could have been much, much later, in fact. But some of the ages that people get out of the Jack Hills, they don't always cluster towards that older age. Many of them are much younger. If we go on to the next slide, I'm going to show you the 4.28. This is the name that I can't pronounce, but I'll try here. Nuvuag Getuk greenstone belt. That's right on the perimeter of Hudson Bay in Canada. And so you can see they call it a belt because it used to be a mountain range, right? And so you can kind of see the bend in that sort of middle part of the image here. And on the next slide, you can see the geologic map for that. And so it was mountainous at one point. And so that's ocean crust that would have been deformed and uplifted later and then folded like that. And so you can see the fold is almost vertical as we look at it in this direction. So it could have been a fold that got refolded also. So the part that we're going to be looking at is the older part there that is, I think, closer to that dark green area there. But anyway, we're going to zoom in on this a little bit and go to the next slide, and you can actually see an outcrop then of what's called a greenstone belt. And greenstone belts, we think, originated in ancient ocean crust. And so if we have in today's ocean crust basalts and microgabbros and layered gabbros and sheeted dikes, in these older rocks like this, they're so metamorphosed, in fact, we just call them greenstone belts. And so here's a greenstone belt where they collected some of this. They ran the neodymium, samarium neodymium ages on it. And as it turns out, it ranges from by 3.7 to 4.28. And so now that's not the actual age of the crystallization of the rock. The samarium neodymium has to be detected first, and then so it's fractionated somehow in this rock. But that age date is more of when the magma was generated. Now remember that ocean crust is relatively thin, right? And I'm sure it was extremely thin when it was back during the Hadean time. And so if you take that ocean crust and you metamorphose it, you turn it into greenstone. That's what they call it in Archean, and in this case would be Hadean sort of ages, but these are actually Archean when they're 3.7. So some recent studies of these rocks have suggested that there are hematite tubules or tubes or filaments in that rock that would indicate there could have been life all the way back for just after the Earth formed, which is just pretty astonishing if you ask me. It gets to be pretty questionable. What do you consider to be evidence of a fossil when you're only looking at tubes and filaments? They found the same thing on Mars meteorites too. So they found some carbon tubes on some of those. And of course, there's some question as to whether they are actually from Mars or from Earth. So anyway, I think that's a question I don't really want to get into for this discussion, but we will talk about the Martian meteorite later on here, not too far in the distance. On the next slide, here's the Slave Province. Now, the Slave Province was named for Great Slave Lake, which is up in it used to be called the Northwest Territory in Canada. And so it's, for a sketchy sort of name, but that's what they call it, so it's called the Slave Province. There are other provinces up there as well. You can see them actually listed on the diagram on the map here. So the Ray Province and the Herm Province, the Superior Province named for Lake Superior. So Slave was named after this Great Slave Lake, and that's up in the northern part of northwest Canada there. And so you see a whole bunch of people standing around this. Now, the Acasta gneiss itself is not that old. So it's only about, it's less than 4 billion years old. But the Acasta gneiss within it has a granite protolith. So in other words, there was a piece of granite that got incorporated into that gneiss that kind of resisted some of the metamorphic pressures that were exerted around it. And so the zircons weren't reset. Their ages weren't reset in this one granite protolith. Sam Bowring came along and he found that granite and he says, I think I can get some zircons out of this. And so he took a piece of that back to MIT, crushed it, of course. And when you crush these things, then you kind of run a Wolfley table, they call it, and you can actually concentrate the heavy minerals that way. I've often thought that they probably get gold out of it as well to fund their research, but that may not be the case. So the zircon's relatively heavy sort of minerals, and those minerals would be collected. And so they'd pick out out of the heavies, they would pick out the zircons, and then you run it through an ICP-S mass spectrometer, inductively coupled plasma mass spectrometer, and you can get out the amount of uranium plus the amount of lead and some of the other daughter products as well. So the uranium lead dates on this gave around a 4.03. Not all of them did, but one of them did. So that was the oldest known rock for a long period of time. So that gets us up to a few images here that kind of make it interesting. The Hadean, here's the planets of it sounds like a Worlds of Fun ride, right? So ride the oceans of magma, you know. Yeah, no, maybe not so fun if you're on it in a boat. But we had this impacts actually generate a lot of heat. So if you can think about two bodies impacting one another, there's heat given off in that. And because you're taking all of that kinetic energy and stopping it instantaneously practically, and most of that energy goes to heat. And so you melt the rocks, right, from impacts. But then also there's another system that's at work here. There's a radioactive isotope of aluminum. And when aluminum decays, aluminum-26 decays, it actually gives off heat as well. And so that's two of the sources of heat that were generated, and that people think that there were oceans of magma for at least a short period of time on Earth. In the next slide here, you can actually see that Theia impactor hitting the earlier version of Earth that would have been slightly smaller than what we are today. And when Theia hits, it left some of its mass behind, and some of that material that then coalesced a little bit farther out in orbit around the Earth formed the moon. In the next slide, you can see some impactors and artist representation, obviously, in each of these, and so showing you what it looked like on early Earth, likely. You can see, like, it looks like basalts, right? So that would be like ocean crust with magma flowing between the oceans. And next slide is more, it looks like a Hawaiian Pahoehoe style eruption. So that looks like a lava, essentially, right, at the Earth's surface there. And that's the Hadean. So that's the beginning of Earth as we well know it. We don't well know it. That's the issue, I guess, here. We have to make models about how we think these things work because, A, there was no witnesses for this, but at the same time, there has to be a natural explanation for this, right? And so everything that we know about impactors and everything about astronomy seems to jive with this idea of a nebular hypothesis. Once that nebulas were discovered, it became easy then to like say, oh, those things could actually come together and maybe form stars. And then they found that actually. So NASA has images of, I think it's called the Horsehead Nebula, and you can actually see stars forming that have recently formed in that nebula. So that's pretty, it's consistent with what we think is happening in astronomy. It's consistent for what we know about Earth and the Earth materials and the materials that are on the moon as well. So that's the Hadean for now. Our next stop on our journey through Earth history, I told you I was going to make you into a time traveler here, right? Our next stop along the way is going to be the Archean. So I'll end it here. And anyway, thanks for your attention. Thanks for letting me take my other class out in the field. And you get to listen to this crazy video instead.